Okay, so let's start. In the last class, I was trying to prove this theorem, which basically gives equivalent conditions for Subgaussianity. Right? So as long as you have a random variable with expected value of x equal to 0, these 5 conditions are equivalent to Subgaussianity. So one condition is that the probability that x is absolute value of x is greater than t is less than or equal to e to the minus t square by k1 square. So the dependence on t is e to the minus some constant times t1 square, which essentially behaves like a Gaussian. Right? So these have Gaussian-like tails. The moments are also upper bounded by the moments of some Gaussian random variable with a certain variance. In addition, the expected value of lambda square x square is less than or equal to e to the some constant times lambda square. And this is sort of almost equivalent to saying that the expected value of x square by some constant is bounded, right? So e to the x square, so the expectation of e to the x square by k4 square is less than or equal to 2. That's the same as saying that the moment generating function is bounded for some value of lambda, right? Maybe not be bounded for all values of lambda, but there is some value of lambda for which the moment generating function of x square is bounded. All right, and it's also equivalent to the first definition of Subgaussian random variables that I gave, which says that the moment generating function is upper bounded by the moment generating function of a Gaussian with some particular variance. So we proved some of these. So first I showed that 1 implies 2, 2 implies 3, 3 implies 4, and I guess towards the end we were going to so I didn't really prove that 4 implies 1, but you can very easily prove that. Instead of showing that 4 implies 5, recall that, right? So we showed the following, that one implies 2, 2 implies 3, 3 implies 4, and I was towards the end I was proving that 3 implies 5, but you can also prove that 4 implies 1, and we'll also see that 5 implies 1. So essentially you have this circular implication which means that all of them are equivalent, right? And again, we were not very careful about optimizing the constant factors. So these k1, k2, k3, k4 and k5 are effectively some constant factors away from each other, and these are not very big constants, 2, 3, 5, 10. But really what we're interested in is knowing how these factors k1, k2, k3 and k4 and k5, they could potentially it could depend on the distribution or the class of distributions that we're interested in, and it is really that dependence that we're interested in. So for example, if you're looking at the variance of if you're looking at x being a Gaussian random variable, then sometimes we're interested in how these constants k1, k2 and so on depend on the variance. So it's okay if it's 2 times the variance or 4 times the variance or 10 times the variance. You're not particularly worried about that, but you want to know what kind of a function it is as a function of the variance. In many applications of interest, that is what really matters, right? Another point is that now throughout I'll essentially be following this particular reference. It's a book by Vershinin called High Dimensional Probability. There's a soft copy of this book available for free, and there's a link to this on the course webpage. Okay, so right, so we're towards the end, we were trying to prove that 3 implies 5, right? Effectively, what I was trying to show is that expected value of lambda square x square is less than or so we know that expected value of lambda square x square is less than or equal to e to the some constant times lambda square for lambda being in a certain range, right? And using this, we were trying to obtain a bound on the moment generating function of x. So we know we have a bound on the moment generating function of x square in some sense, and we're trying to obtain a bound on the moment generating function of x for all lambda, for all real valued lambda. And we were trying to do this in 2 steps effectively. So the first step, we assume that lambda is sufficiently small, it's not too large. And in this case, we used the following bound, e to the x less than or equal to x plus e to the x square. And if you use this, then e to the expected value of e to the lambda x is basically less than or equal to expected value of lambda x plus e to the lambda square x square. This is what we showed. And since x is a zero mean random variable, the first term is 0. And the second term from the bound we have over here is less than or equal to e to the k3 square lambda square. Right? So we have this bound for only for lambda being sufficiently small. Right? And we want a general bound on expected value of e to the lambda x for all lambda. So now let's consider the other case where lambda is greater than, absolute value of lambda is greater than 1 over k3, right? So again, we'll make use of the same bound. So we'll make use of the bound that 2 lambda x is less than or equal to k3 square lambda square plus x square by k3 square, right? And we got this bound essentially by looking at the square. Right? So k3 lambda minus x by k3 the whole square is greater than or equal to 0, which implies that k3 square lambda square plus x square by k3 square is greater than or equal to 2 lambda x. Right? So this was roughly where we stopped in the last class. So if I take expected value of e to the lambda x just as before, then again I get expected value of e to the k3 lambda square by 2 times e to the x square by 2k3 square. Okay, great. So this term anyway doesn't involve x, so I can just take it outside. So it's e to the k3 square lambda square by 2 times expected value of x square by 2k3 square, right? But I already have a bound on this particular quantity, right? Because I know that from the property that I have, expected value of e to the lambda square x square is less than or equal to e to the x square times k3 square, as long as absolute value of lambda is less than or equal to 1 e to the lambda square k3 square. So this is what I have. E to the expected value of e to the lambda square x square is less than or equal to e to the lambda square k3 square for all lambda less than or equal to 1 over k3. And in this case, I have lambda to be 1 over 2 times or square root 2 times k3. Right? So I can just plug this in here, and I get this to be less than or equal to e to the k3 square times 1 by 2k3 square. Right? So I'm just taking lambda to be, or lambda square to be 1 by 2k3 square in this case, right? So this k3 square gets cancelled, so it is e to the half, correct? So this quantity is just e to the k3 square lambda square by 2 times e to the half, right? Is it okay so far? Right, but right now I'm assuming that k3 square lambda square is greater than or equal to 1, right? Basically, I'm looking at the case where k3 lambda is greater than 1, or k3 square lambda square is greater than 1. So e to the half, so this quantity is less than or equal to e to the k3 square lambda square divided by 2. Do you agree? Because I'm looking at the regime where k3 square lambda square is greater than or equal to 1. Correct? So I get e to the k3 square lambda square by 2 times e to the k3 square lambda square by 2, which is just e to the k3 square lambda square. Okay. So the first part, I have expected value of e to the lambda x, the moment generating function, to be less than or equal to e to the k3 square lambda square for all lambda less than or equal to 1 by k3. And now I have the moment generating function to be less than or equal to e to the k3 square lambda square for all lambda greater than or equal to 1 over k3. Right? So the moment generating function is upper bounded by e to the k3 square lambda square for all lambda in R. Right? So that completes the proof that 3 implies 4. Now, again, in the notes, I have the proof of the fact that the fourth property implies the first property. And I'll also leave it as an exercise for you to show that the fifth property implies the first property. Basically, if I have a bound on the moment generating function, then the probability, the tail probability is upper bounded by e to the minus t square divided by some constant. Right? Again, that's fairly straightforward. You just use Chernoff bound and carefully choose lambda. Right? That's all there is to it, and that's not too hard. Right? But really, what I want to focus on are applications of these properties, right? And let's get into that. Now, there were some sort of inequalities that I used in between without giving a proof. Again, the notes contain the proofs of some of these inequalities. I will leave you to go through it. But now let's take a few examples. Right? Let's look at some examples of subgaussian distributions. We've already seen that the Bernoulli distribution and the Gaussian distributions are subgaussian. The Gaussian, of course, trivially. And Bernoulli as well, we saw that the Bernoulli random variable is also subgaussian. But now let's look at a general bounded random variable. Okay, so let's suppose that x takes values in some particular interval between alpha and beta. All right, and let's further assume that the expected value of x is equal to 0. All right, what can you say about alpha and beta in this case? Correct. So which essentially means that alpha should be less than or equal to 0 and beta should be greater than or equal to 0. Right? That's something we need to have, otherwise we can't have the expected value of x to be equal to 0. Okay. Now we want to show that this random variable is subgaussian. Okay. And we want some estimate of what these constants look like, k1, k2, k3, k4, as a function of alpha and beta. Right? Okay, so what do you think would be the best way to go about this? I'm not giving you any other information except the fact that x is bounded. It could be any distribution. Okay, not necessarily a uniform distribution or anything. Okay, let's just quickly look at the properties once again. Right? Maybe I'll just write it down for convenience. Right, so these are the properties that we have. And I want to find whether a bounded random variable is Subgaussian or not. Any guesses which would be the easiest property to look at?
We go to proof of 3 to 5 on.
3 to 5, okay. 3 to 5, yes. The first part or the second part?
This part.
Okay.
The bound expectation of either x squared into k3 squared.
Correct.
You assume the lambda is bounded.
Correct.
But if you want to prove this for all lambda, this for all lambda.
Okay. So maybe again it's overuse of notation over here in this case. So I'm looking at this. I'm just bounding this particular quantity, right? So this is expected value of some lambda prime square x square, where lambda prime equal to 1 over k3, 2k3 square. Right? So maybe I should call this lambda bar or lambda prime or something. Okay, so the lambda over here is different from the lambda here. That's the thing to keep in mind. Again, that's what I've reused notation, which probably is the source of confusion. That's okay. Any other questions? Okay. All right. So now we want to check whether bounded, in general, bounded random variables are Subgaussian or not. Okay. And I want to make use of one of these properties. I know nothing else. I don't know anything in addition to the fact that x lies in the interval alpha to beta. Okay, property 4. It's good. Let's try that out. Okay. What I want to show is that expected value of e to the lambda square. Property 4 says that x square by k4 square is less than or equal to 2 for some constant k4. If I'm able to show this, then it's going to be Subgaussian with variance factor some constant times k4 square. Right? Can I prove this? So essentially, I want an upper bound on e to the x square by k4 square. Expected value e to the x square by k4 square. But I know that x is bounded in a certain range. So can I use a simple upper bound for this particular quantity? Great. So let's use that. So x square, so I know that x lies between alpha and beta. So x square is less than or equal to the maximum value of alpha square and beta square. Correct? So this is less than or equal to e raised to max of alpha square beta square divided by k4 square. Correct? Okay, and this I can choose a k4 such that this is less than or equal to 2. Correct? What would k4 be? Yep. So as long as k4 square, I can choose k4 square to be the max of alpha square beta square divided by log 2. Correct? Okay, so that's great. So this implies that x is Subgaussian. So all bounded random variables are Subgaussian. And that's going to be very helpful later on in some of the applications that we will see. Okay. So we know that Bernoulli random variables are Subgaussian, bounded random variables are Subgaussian, which actually implies that Bernoulli random variables should also be Subgaussian. All right. Let's look at another example. Let's take the exponential random variable. Okay, so let's fix some constant alpha greater than 0. And we look at the following density: fx of x is equal to 0 for x less than 0, and it's 1 by alpha e to the minus x by alpha for x greater than or equal to 0. Okay. Or if you want to look at a zero mean random variable, I might as well look at fx of x. I can look at the symmetrized version if you want. This is called the Laplacian random variable. So it is 1 by 2 alpha e to the minus absolute value of x divided by alpha for all x in. Okay. Now I want to check whether this random variable, either of these for that matter, is Subgaussian or not. Okay, let's maybe take this one because it's zero mean. Again, which one would do you think we could use? Yeah, 5. Sure, I could look at 5, but I might also look at 4 itself, right? Because I'm not sure. The problem with the other properties is that I have to make sure that I use the best possible bounds, right? Which may or may not be easy in general. But then 4 is slightly easier to look at because all I need to show is that quantity is bounded or not. If it is bounded, then it's Subgaussian. If it's unbounded, then it's not Subgaussian. Right? So again, there are different approaches, but let's use 4 again. So I have e to the expected value of e to the x square by k4 square. So integral from minus infinity to plus infinity 1 over 2 alpha e to the minus absolute value of x divided by alpha times e to the x square divided by k4 square dx. But this is really symmetric in x, right? So this is effectively equal to 2 times 1 over 2 alpha integral 0 to infinity e to the x square by k4 square e to the minus x by alpha dx. Okay, so these 2 and 2 get cancelled. How do you think I could handle this particular integral? Correct. So basically I want to reduce it to the PDF of a Gaussian because I know that the integral of the PDF of a Gaussian should be equal to 1. So that's a standard trick. This is integral 0 to infinity e raised to x square by k4 square minus x by alpha plus something else. Okay, so it is k4 square by 4 alpha square. Let's just check. Plus k4 square minus over alpha square dx, right? That's what you would try to do. So this is equal to 1 over alpha e to the, let me take this quantity outside. So e to the minus k4 square by 4 alpha square integral 0 to infinity. Now this is some constant, it's bounded. Integral 0 to infinity e raised to x by k4 minus k4 divided by 2 alpha the whole square dx, right? What can I say about the integral? Is the integral bounded? Are you sure? It depends on how many say it's bounded, how many say it is unbounded, and why is it unbounded? Yeah, so the sign, you should make note of the sign in the exponent, right? It's positive. So e to the x minus some constant the whole square, right? So this is in fact unbounded, right? So no matter what value of alpha you choose, this is always going to be unbounded. Right, so the exponential distribution is in fact not Subgaussian. In fact, the whole class of gamma distributions is unbounded. It is not Subgaussian. Okay, and we'll really investigate gamma distributions in detail later on. But before that, let's see some applications. So far, we've only seen examples and properties of Subgaussian distributions. Let's now see how we can use these concentration inequalities for a different problem, right? But before that, any questions? All right. Yeah. No. So I'm saying that the exponential distribution is a special case of the gamma distribution for certain parameter. And I'm saying that the whole family of gamma distributions is Subgaussian. You can prove that separately. Okay. In fact, we'll see another class of distributions called subgamma distributions, for which the moment generating function is bounded by the MGF of some gamma distribution. Just like we have Subgaussian distribution, we'll see subgamma distributions. So for Subgaussian distributions, as we've seen, the moment generating function is upper bounded by e to the lambda square k phi square for all lambda in R. But then for subgamma distributions, we'll see that this is true only for lambda lying in a certain interval. And that for Subgaussian distribution, the tail bound takes the form e to the minus t square divided by something. But then, as you can see, just by looking at the density over here, you can guess that the tail bound would take the form e to the minus t times some constant, not e to the minus t square times some constant. Because although this PDF decays exponentially, it doesn't decay exponentially that fast. It doesn't decay exponentially as fast as a Gaussian. Okay, so let's see an application which is sort of very useful in data science and machine learning. All right, so this is a problem of dimensionality reduction. Okay, the problem is the following. Well, in many cases, you have like very large data sets, and you want to perform some kind of processing on these data sets. These data sets typically consist of very high dimensional vectors, and you want to do some kind of processing over these particular vectors. Sometimes you want to do clustering, sometimes you want to know whether two vectors are similar to each other, and so on and so forth. Right? And all of these operations have to be performed in this high dimensional space. Right? But in applications, working with high dimensional spaces is larger. So typically what you do is you try to reduce the dimensionality of these vectors while preserving some properties of the original vectors. Right? So you have these whatever n dimensional vectors, you try to bring it down to some t dimensional vector somehow by projecting it down to a lower dimensional subspace. But then this projection won't be lossless, right? There might be some loss in doing so. But at the same time, there are some properties that you would still like to preserve. Okay? So one common feature that you would like to preserve is the pairwise distances between points. Okay? And that's useful when you want to check for similarity between vectors, or sometimes when you want to do nearest neighbor search or clustering, you're using Euclidean distances and so on. Right? So we are given, let us say, m vectors. Right, where each vector lies in a capital N dimensional space. Okay, and I want to somehow design a projection which is basically a mapping from, let's say, n dimensional space to little n dimensional space, such that somehow the distance between points is preserved. If I look at the distance between f of xi and f of xj, this is, let's say, approximately equal to the distance between xi and xj. Okay. And this is particularly useful, let's say, if you want to perform Euclidean distance kind of operations over this. For example, suppose I'm given, say, m points, and I want to find the closest point in this set to the first vector. Okay. I could, of course, compute the minimum distance to each of these points, but then now the number of operations, what would be the total number of arithmetic operations required? Yeah, m minus 1, but each operation takes, what is the cost of each operation? N, so capital N, so I'd require roughly whatever order n m operations if I were to perform these operations in Rn. But if I project it down to a smaller subspace, and let's say I have this particular property, then the total number of operations goes down to little n times m. Right? So the smaller little n is, the better it is for me, because my computational complexity goes down that much. It's also useful if I want to store these particular vectors, because once again, the total number, so in this case, I would have to store nm real numbers. But now if I only have to store the projected vectors, then I only have to store small n times m many real numbers. All right, so this gives me savings both in terms of computation as well as space. Correct? So the natural question is, okay, so if I want this approximate distance guarantee, then what is the smallest n I can project this space down to? Okay. What is the smallest dimensional subspace to which I can project these m vectors down to? All right, is this problem is okay, right? Okay, so in general, if you had to guess, what do you think small n would depend on? It would depend on capital N, right? It would depend on m, right? And potentially also depend on whatever the parameters that define this approximate distance guarantee. Okay, so in particular, I want that, let's say, f of xi minus f of xj, this should be less than or equal to some 1 plus epsilon times the norm of xi minus xj, and greater than or equal to 1 minus epsilon times norm of xi minus xj. Okay, so this is the guarantee that I want. So naturally, you would expect that the best little n that I can achieve depends on capital N, capital M, and epsilon. Does that sound fair? Okay, but here's a very surprising result, that you can actually do this, but the small n depends only on capital M and epsilon. It's fully independent of capital N. So your original space could be like a really large dimensional space, maybe like a billion. But as long as you don't have too many points, let's say you have 1 million points in a billion dimensions, and I have a certain epsilon, then I can actually project it down to a very, very much smaller dimensional subspace, which is completely in the size of the subspace is independent of the original space, the dimension of the original space. Okay, but the point to keep in mind is that it depends on the number of points as well as epsilon. So if, for example, if I have the exponential in n number of points m, right? If suppose that m is equal to some 2 to the n, then I don't really get much savings here, right? But as long as, let's say, m is at least polynomial in n, this quantity turns out to be much, much smaller than capital N. Okay, so this is called the Johnson-Lindenstrauss lemma, and it says the following. So if I fix an epsilon greater than 0, and I have m points all living in R capital N, then it's possible to construct a function f that maps Rn to R little n such that these distances are the pairwise distances are approximately preserved. Another nice feature is that this function or map can be chosen to be a linear map. All right. So it's possible to construct a linear transformation, basically a projection matrix, such that, okay, it's not exactly a projection matrix, but it's a matrix from R, basically a small n by capital N matrix, such that after transformation, the distances are still approximately preserved. Right? So in fact, how do you prove that such a matrix in fact even exists? So the technique we'll use is what is called the probabilistic method. So I don't know whether such a matrix exists or whether such a map exists. So I'll just take a random map. I'll take a random matrix and see what happens under the influence of a random matrix. If I can show that with some positive probability good things happen, then it must mean that there is at least one matrix for which good things happen. Right? Because I know that it happens with positive probability. So there should exist at least one matrix for which this property is satisfied. Correct? So let us choose a matrix G bar, which is an n by n matrix with IID Gaussian entries. So every entry of this G bar matrix is a Gaussian random variable with 0 mean and variance equal to 1. Okay, I'll scale it down so that 1 by square root of n, so that effectively each row has norm equal to 1, expected norm equal to 1. Right? So my map is basically just going to be this linear transformation, nothing else. And the property I want to show is that, in fact, with high probability, this linear transformation preserves distances. Okay. So in fact, let us see what happens under such an operation. So let me take an arbitrary vector x. So take any vector x in Rn and let me define y to be g times x. Okay, let's see what this behaves. How does this behave? So the ith entry, what is it in terms of the entries of G and the entries of X? So this is just equal to Gij Xj, correct? Now X is some vector, okay? Let me use X of J. Right? X is some vector and Gij's are IID Gaussian random variables. So what can I say about y of I? what would be the distribution of y of I? It would be Gaussian. Good. What would be the mean of y of I? So each Gij is a zero mean Gaussian random variable. I'm taking a linear combination of zero mean Gaussian random variables. So that should also be a zero mean Gaussian random variable. So expected value of y of I is equal to 0, right? This is equal to summation j equal to 1 to n Gij bar divided by n x of j, right? Where Gij bar is basically Gaussian with zero mean and variance 1. Correct? Okay, in this case, what is the variance of y of I? So it's a sum of independent Gaussian random variables, not identically distributed. If I look at this quantity, right? So each random variable is scaled by x of j divided by square root of n. So the variance of this random variable is the sum of these variances, and that is simply equal to 1 over n times the norm of x squared, right? So it's equal to 1 over n times summation over all j x of j the whole square, which is just the norm square divided by n. You all agree? Okay, so what can you say about the norm of the average norm square of the vector y? Yeah. Correct. So it's just the square norm. So I takes values in the range 1 to small n. So the norm square of y is equal to summation I going from 1 through n of equal to n expectation y of I squared, which is just the norm of x squared. So in expectation, this map really preserves the squared norm, correct? So now if this also concentrates, then basically I'm done, right? So what is the probability that norm y squared is, so I can ask the following question. I know that on average, the norm squared of y is equal to the norm squared of x. So, and again, this is a function of sums of independent Gaussian random variables. So I can ask the question, what is the probability that it lies within an epsilon of the norm squared? Correct. I can find a bound for this particular quantity. Now, this of course would depend on small n, right? Let's say I want to know what is the smallest n for which this quantity is less than or equal to, greater than or equal to 1 minus delta. For some constant delta or some function delta, let me call this delta sub n. Okay, or in other words, I want a tight lower bound on this particular quantity. In fact, again, these are sub-Gaussian, it's a function of Gaussian random variables. So we can expect that this in fact behaves like 1 minus 2 to the negative some constant times n epsilon square. Okay, again, this is not a proof, but let's start with this as a claim. Okay, now suppose this is true. Okay, so the probability, let me call this event a of x. So the probability that a of x happens for a given x, the probability that this happens is at least 1 minus 2 to the minus some constant times n epsilon square, or the probability that a of x is not true, does not happen, is less than or equal to 2 to the minus some constant times n epsilon square. Okay, now this is for a given x, right? But what I want is slightly different. I want to ensure that all pairwise distances are approximately guaranteed, right? So I can also look at what is the probability for a given pair xi minus xj is not true. Right? So I take one pair xi and xj, and I ask the question, what is the probability that the distance, the pairwise distance between the two after transformation is not equal to the pairwise distance between them before transformation? Right? Again, for this, I know that this is less than or equal to 2 to the minus constant times n epsilon square for a given pair ij. But how many pairs are there? Yeah, MC2, right? There are m points. So what is the probability that this does not happen for any one of the m? Now I can basically use a union bound and upper bound this by m choose 2 times this particular quantity, and basically then choose the smallest n for which this quantity is upper bounded by. So let's stop here and continue in the next class. But you get the at least the general flavor of how you use these tools to show that there existence.